Hello, everyone. Welcome to the OpenFOAM and the Combustion Simulation webinar. So today we are very happy to have Professor Mohsen Talei to join the webinar, and he will give us a presentation about insights from perturbed laminar premixed flames. So before the presentation, I will first introduce the Professor Talei. Professor Talei is a former discovery early career researcher of the Australian Research Council, and he is an associate professor in the Department of Mechanical Engineering at the University of Melbourne. Professor Talei joined the University of Melbourne as a staff member in 2014, having previously completed a postdoc research at the University of New South Wales and a PhD at the University of Melbourne. Professor Talei has 18 years of industrial and academia research experience in the broad area of energy, with a focus on low-emission energy technologies. Professor Talei's research involves a significant use of high-performance computing to develop reliable models that can be used for simulating cleaner gas turbines and engines. So now the time is yours, Professor Talei. Thank you very much.
Yeah. Thank you so much for the invitation. I appreciate that. And thank you for the introduction. So as you can see, the title of my talk is Insights from Perturbed Laminar Premixed Flames. And I'm not suggesting that we have to stop working on turbulent flames, but hopefully in this presentation, I can convince you that there are benefits in using these types of flames to learn from them and also get ideas about what we can do as the next stage. Okay, so just a bit of introduction about our group and what we do at Melbourne University. So the numerical simulation that we perform, they're mainly relevant to gas turbines and reciprocating engines. If I focus on gas turbines, the topics that we are interested in and we've been working on are sound generation by premixed flames, which are quite relevant when we study thermoacoustic instability in gas turbines, which will be discussed today. Flame wall interaction and flame cooling air interaction is another issue that we are working on. And again, this is a topic that I will cover in today's presentation. Diluted flames with hot combustion products is another topic related to gas turbines, which is an idea to reduce emissions. But when you have these types of flames in the presence of a relatively cold wall, you might not achieve what you are aiming for. When we talk about reciprocating engines, our simulation framework is slightly different. We mainly use a commercial software which allows us to simulate real engines. So in the thermodynamics lab, we have quite a bit of experience on these engines, and we have experimental data and very good collaboration with experimentalists. So we are able to simulate these engines and understand the physics and try to optimize the combustion process. So the two areas related to reciprocating engines are natural gas injection. So we are interested in spark ignition engines mainly, and an advanced technology which is basically using direct injection of the fuel into the combustion chamber in order to improve the volumetric efficiency. But obviously, because you do that, you have to have a good control over your mixture quality to get a very good combustion. So that's one area. And then engine knock, which is an issue limiting us from having more efficient spark ignition engines, and we work on that. Especially, this is a problem relevant to hydrogen, and we have done some work in relation to that. So generally, combustion modeling is needed for any type of simulation of a gas turbine or engine, largely simulation or RANs. And one approach we have used here is to use gene expression programming. We've done some work to develop improved combustion models. And obviously alternative fuels and including hydrogen is another topic that we are looking at to understand how combustion properties of hydrogen can impact the flames and also the performance of the end users. So that was a summary of the work that we do. I'm going to talk about the motivation now for the studies that I'm going to present today. So the two issues, key issues which are related to gas turbines and stop us from making them more efficient and cleaner. One of these issues is called combustion instability, which is a problem in low NOx emission gas turbines when we want to use lean premixed flames. That problem starts because flames generate sound, and that sound can interact with the boundary conditions and then reflects back to the flame, and the interaction of the sound waves with the flame can make it unstable. If this instability is not controlled, it can result in the combustor failure, and obviously it makes a very loud noise. So this is one issue that doesn't allow us to have cleaner gas turbines, and it can become a problem for hydrogen, as I will explain later. Another issue is CO emissions. So the graph that I've got on the right-hand side on this slide shows you how two important forms of emissions, CO and NOx, vary as a function of equivalence ratio on the lean side of the operation. Okay, so you can see that as equivalence ratio increases, NOx emissions goes up as you expect, because you've got temperature controlling NOx emissions in this case. But we have another problem, which is when we make the mixture leaner, and this is what we are aiming for, then you can see increase in CO emissions, and this is also something that you want to avoid. What is not shown in this graph is that when you're looking at lean conditions, you might also get thermoacoustic instability. So as you go linear, it's not clear which problem comes first. You might get an issue with CO emissions, or you might have an issue with thermoacoustic instability. Either way, you'll have a limited range of operations in a gas turbines, and what you're trying to do is to actually work close to those limits. You want to make the mixture as lean as possible to improve efficiency. At the same time, you want to have a stable combustion. You want to generate a very minimum, the minimum amount of NOx and CO. So the two phenomena which are important for these problems are combustion noise, which is a topic of today's presentation, and also quenching of the combustion product, which is suggested to be one reason for having CO emissions. So when you have, for example, combustion products touching a relatively cold wall, that can quench the flame or quench the combustion product and increases CO. So two examples that I will discuss today include sound generation by premixed flames and CO emission due to flame cooling air interaction. So in a gas turbine, you also use cooling air to make sure that the wall does not overheat. And we want to look at how CO emissions will be affected by cooling air. So the purpose of this talk is to focus on laminar premixed flames, but also I'm going to show you how the insights from those laminar flames can be used to understand what might happen in turbulent flame. So we can do direct numerical simulation to study these phenomena in detail. It allows us to resolve all the length and time scales of the problem. And through these studies, we can also look at the implications of the findings for modeling, okay? So that's what basically what I'm going to talk about today. So let's talk about the first example. How do premixed flames, especially the laminar ones which you perturb, they generate sound? So this is a picture, I would say, work of art by a former PhD student that we have, Dr. Samuel Weisman. He's currently a research fellow at NTNU. And what he did was basically using a laminar premixed flames, and he had the opportunity to perturb it with a speaker underneath. So the speaker allows you to excite the flame for a range of frequencies and amplitude. And one of the things he did was to have a bit of fun with this flame. So you can see you get all sorts of shapes depending on how you excite this flame, and also depending on how you apply the boundary condition. For example, you can have a glass around it to confine it, or you can have an open flame without the glass. Okay, so one of the reasons I put this slide is that the possibilities are endless when you have a laminar flame. Okay, it is the starting point is laminar, but as you increase perturbation, you can actually get something which is close to a turbulent flame. All right, so I'm gonna talk about the DNS study, and this is an attempt to simulate a laminar flame which is excited at the inflow. For this DNS study, we wanted to make sure that the computational domain is sufficiently large to allow the acoustic waves generated by the flame to leave the domain without creating any issues. So you can see, let me just use my pointer to explain what we have in this problem. So because it's a laminar flame, it's a 2D problem, we use a symmetry line in the middle just to simulate half of the flame. We introduce fuel and air from the bottom, and then we use velocity perturbation with an amplitude of 25% to force the flame and see how the flame responds to their perturbations, and also how sound is being generated depending on the frequency of excitation. The conditions that we have chosen, not completely relevant to gas turbines, but we try to make some parameters more relevant to the conditions that we have in a real flame. So this is an animation of how the flame responds to velocity perturbations at the inlet depending on the frequency. So for all of these cases, the amplitude is the same. What we do, we change the frequency of excitation. So the picture, the animation that we have on the left-hand side is when you have the highest frequency. As a result of that, the flame doesn't respond because the time scale of the excitation is very short. But as you have a time scale of the excitation being comparable to the flame time, you start to see wrinkling on the flame surface. As you go to lower frequencies, that wrinkling is going to be even creating more disturbance to the flame, and it's going to be longer in terms of wavelengths. So one phenomenon that you can see for intermediate frequency is what we call a flame pinch-off. So you have a pocket of unburned gas getting detached from the flame, and it's going to be consumed further downstream. When you have very low frequency, which is the animation on the right-hand side, then the flame is just expand and retracts in a quasi-steady manner. You don't see these flame pinch-off and what we call oil and burnout events anymore. Okay, so they just happen for a limited range of frequencies. So this is exciting because when we look at the acoustic field for the intermediate frequency case, we can see how these phenomena will contribute to the generated sound in the far field. So what I'm showing here is an animation of the dilatation field. The dilatation is the term that acousticians usually use to look at the acoustic field. And you can show that it can be proportional to pressure fluctuations. The nice thing about this quantity is that you can also see the flame surface on the same plot. So what you can see is the pressure waves being generated by the flame, but especially if you look at these events, when you have flame pinch off, you can see it's a source of sound, and then when the island bends out towards the end, you have another sound source. Okay, so this is insightful, but the question is, okay, these are laminar flames. Do we have these events happening in a turbulent flame? Okay, so now that we have this insight, is it really useful? So the next step for us was to look at a turbulent premixed flame. We've done some analysis on the laminar flame, looked at some called configurations as well, and developed some theory. But one of the things that we are very interested in to see whether the same thing happens in a turbulent premixed flame. So again, we use the direct numerical simulation. And in this case, we have done simulation of two equivalence ratios, 1 and 0.7. We have chosen the parameters such that the Reynolds number is the same between the two cases. And the mixture is basically methane air, okay? In order to make sure that we have the right boundary condition, we used another DNS study to impose the right profiles at the inflow. The challenge we had for a turbulent premixed flame was to make sure that we don't get any reflection from the outflow. So it was even harder than a laminar flame. And what we had to do was, on top of having non-reflecting outflow boundary conditions, we also had to use what we call a sponge layer to make sure the acoustic waves are damped before they create any issues inside the domain, okay? And obviously, when you do a DNS of a turbulent premixed flame, it's gonna be very costly. So we were limited to doing only 2 cases here. So now let's look at the dilatation field. And I'm just showing you so the stoichiometric case, all right? So it's a turbulent flame. It's hard to see what's happening in terms of the flame itself, but you can actually see the signature of these monopolar sound sources across the flame. So not just happening at the tip, but you can see kind of from the beginning, there are some monopolar sources of sound in this premixed flame. And you can see how they interact with each other and how they propagate to the far field. So in terms of visualization, we can actually pick a few of these spherical waves and trace them back to see what is actually causing the sound. What we've done is just select the 3 spherical waves here. So I call it A1, A2, and A3. And we look at, you know, where these waves are coming from, okay? So if I look at A1, that's basically a pocket burnout close to the flame tip. So it's very similar to the island burnout event that we had for the laminar case. So they are quite often, and this is a significant sound source. What is interesting is that if you look at some of the past experimental studies, they report that the flame tip is a very strong sound source, but in the experiment, they were not able to actually demonstrate what is causing that sound from the flame tip. So, and we reckon that this is basically the main mechanism contributing to the generated sound close to the flame tip. So if I focus on event A2, what we can see here is that the flame pinch-off event is not as neat as what we had in a laminar flame, but when you have, you know, that basically collapse of the flame neck, you get strong sound wave being generated. Okay, so we can see that type of event in a turbulent flame as well. And the third type of phenomenon that we identified from visualization is what we call the tunnel formation. So when you have 2 flame surfaces touching each other, and that creates a hole in the middle of the flame, that's basically a tunnel formation event. and that is also a source of sound. So we didn't have this kind of event in a laminar flame, but you can imagine this is like more like a laminar flame, a 1D laminar flame annihilation, but obviously it's not completely 1D. You have also, you know, a bit of curvature involved around this event. Okay, so this is all good. You know, we've done some visualization and it looks like that we've got lots of these events contributed to the generated sound. But then the key question is, okay, you know, how important are they in terms of the overall generated sound? Are they really contributing to the total generated sound, or they're just random events creating a bit of noise? So in order to quantify their significance, we had to use an algorithm to identify them automatically. And we did that based on the gradient of the progress variable field. So if you consider two flame surfaces touching each other, at the points that they touch each other, the gradient of C is going to be 0. So that's, and this is what we call a critical point, okay? So we, based on some threshold on the progress variable field and also the gradient of C values, we were able to identify these events. We developed an algorithm that we could track them in time. And we also tried to isolate them from the rest of the flame surface to look at how much sound they generate. And obviously this is going to be quite challenging because it's really hard to draw a line around the annihilation event and say, okay, this is the boundary. We had to actually do a bit of sensitivity study to understand whether that is achievable. So based on that study, you have to form a Hessian matrix, and based on the sign of the eigenvalues of that matrix, you can identify the different events automatically. Okay, so we had the so one of the events is a reactant pocket, which is not present in a premixed flame. You don't have any like an ignition kind of event here. We had the tunnel formation, we had the tunnel closure, the pocket burnout that I already introduced, and we identified the fourth type of event here, which we called it multi-feature. So basically, what we saw in the turbulent flame is that these multi-feature events are quite common. And what happens is that when you have different types of annihilation events happening close to each other, both in space and in time. So you might have a flame pinch-off creating an island burnout, but because they're so close to each other, they kind of happen at the same time. So it's really hard to say, okay, this is your pinch-off and this is your island burnout. So we called it a multi-feature event. So the graph that you see on the right-hand side, that shows you the distribution of different types of events, okay? So the pocket burnout, we have basically a lot of them close to the flame tip. So the dashed line here shows the average position of the pocket burnout event. It doesn't mean that you don't have it close to the inlet. So you might have few of them happening close to the inlet, but they are mainly happening close to the flame tip. The tunnel closure event, you can see that they happen quite a bit across the flame. You have the tunnel formation happens closer to the inlet, and the multi-feature event just happens everywhere in the flame, okay? So this allows us to identify the contribution of different types and also put them together to see how much sound they generate. So in order to estimate how much sound they generate, we had to use another theoretical framework. So those who work on acoustics, they are familiar with the concept of acoustic analogy. This is basically a form of wave equation, which is derived from your governing equations, but it's a simplification of those equations. And because it's a wave equation, you can interpret the right-hand side of that wave equation as a sound source, okay? The most popular acoustic analogy is Lighthill's acoustic analogy, which is a rearrangement of continuity and momentum equation, okay? So if you do that, you get a wave equation on the left-hand side, and you get a bunch of source terms on the right-hand side. In a turbulent non-reacting flow, the first term is dominant, but in a combusting flow, people have shown that the second term, which is the second time derivative of what we call the excess density term, is actually the dominant sound source in some cases, not always. So there is an approximation that people use for combusting flows, and we decided to use that approximation. We have already verified that this approximation works for the entire flame that we have studied in this paper. And in that formulation, the right-hand side simplifies to the time derivative of the heat release rate, okay? Not the heat release rate, the time derivative. So when you have fluctuations of that quantity, you're gonna get pressure waves being generated, okay? You can solve that wave equation using Green's function solutions. And in 3D, the Green's function solution is quite simple. You just basically multiply the time derivative by the volume of each cell, and then depending on the distance, your pressure fluctuations can be estimated, all right? So now let's look at what we get when we apply this framework. The plot that I've got on the right-hand side shows you the sound pressure level for the two cases. So what we can see on the top is equivalence ratio of 1, and then this is the bottom is showing you the equivalence ratio of 0.7. The solid line is the DNS. So if I have a probe in the far field, when I say far field, relatively far from the flame, when you do DNS, you cannot be really far. That's what the solid line shows you. So you can see that at low frequency, you have high amplitude, and as you go to high frequency, you have a drop-off, which is the expected trend. If I put together the generated sound by these annihilation events, I get the dashed line. And you can see for the stoichiometric case, in the high frequency region, we have a really good match, okay? So, and the match is good when this non-dimensional frequency, which we call it a Struhal number, that's based on the flame diameter and also the inlet velocity, is slightly above 1. Okay, so that ST equals 1 seems to be the boundary that you can choose for annihilation events. So the question is, why is that the case? If I also review what's happening in the Lin case, the same thing happens, but then you go to very high frequency, you see that actually the annihilation events produce more sound than the DNS. That doesn't make sense. But what we concluded after a lot of investigation is that the limitation of the algorithm doesn't allow us to capture this part of the spectrum properly, because as I said, we have an issue in identifying the annihilation event in terms of boundary. Where should we really put the circle around them? And when you go to lean conditions, that becomes even harder because they are weaker sound sources. Okay, so let me go back to this Struhal number 1 story here, okay? These annihilation events are very fast time scale events. When you have two flame surfaces meeting each other, you will have acceleration of the flame surfaces, because the untrapped mass between the two flames is going to be heated up by both flames, and then the acceleration increases the displacement speed, and then when they completely meet each other at the center, it will go to infinity. So that's what happens for the displacement speed. So fast time scale means that you would expect these events to produce high frequency sound, and this is what's happening here. So they are responsible for the high frequency part of the spectrum. However, that doesn't mean that they don't do anything on the low frequency side. They cannot explain everything. You can see there is about 20 decibel difference, 20 decibels difference between the two curves here, but they still make sound. And the reason they also contribute to the low frequency sound is that when you have a bunch of random point sources, obviously they can create some low frequency sun when they interact with each other. Okay, so that was again an interesting observation. So we were able to see how these flame interaction events create noise, and also how important they are in a turbulent flame. And now I'm going to move on to the modeling side of it. So in a real device, we cannot use DNS. We are interested in other simulation tools, such as larger simulation and RANs. So we picked a combustion model, which is based on the flame geometry, and is quite popular. It's called flame surface density modeling. And the idea is that if you have the progress variable equation, which I'm showing you here, and you filter it, the right-hand side of the progress variable, you can actually replace it by a model. So instead of trying to estimate the filtered reaction rate, you can just get rid of the whole right-hand side. So you can combine reaction and diffusion term into one term, and then try to model that. Okay. So in your LES or RANS, then you can just solve this equation with a model for what we call the flame surface density. The common model that is used is the following. So you've got the filtered flame front displacement term described as a function of sigma gen, which is basically your based on the wrinkling factor, you can estimate it. And then a factor here, which is usually assumed to be equal to rho USL. So it's a surface average displacement speed, okay? So in a DNS study, what we want to do first is to actually see how this modeling assumption will impact the generated sound. And obviously, this is going to be challenging because we need to make a relationship between the importance or the impact of our model and on the flame itself, and also the generated sound from that flame. So we decided to use the same framework as before, which is acoustic analogy. And if we use that framework, the pressure fluctuations in the far field is a function of the fluctuations of the filtered reaction rate. If I apply the same thinking here as a progress variable equation, I can replace that term by my flame surface density model, as well as the diffusion term here. And in the literature, people ignore that diffusion term, and when it comes to combustion noise, and it is argued that the time derivative of this term is actually more important when it comes to the fluctuations of the reaction rate. Whether that's true or not, that's another topic for discussion, but let's just assume that we want to look at the importance of this modeling to the generated sound. So even if the diffusion term is actually important and cannot be neglected, we want to look at the impact of this modeling in isolation. So you can immediately see that if previously I had a problem of modeling this term properly, and I was struggling to get the right answer, now I have to get the time derivative of that term right. Okay, so it can be quite challenging to do that. So I can then calculate the pressure fluctuations both from the DNS term as well as the estimated one from the model. Okay, so let's look at some results of the model itself, the model that we use for flame surface density. We picked 3 different models that are cited in the literature as reasonably good models, like they perform reasonably well. I'm not saying that other models do not perform well, but some recent studies have shown that these models are actually good candidates. So what I'm showing you here on the right-hand side is quite a busy graph, but I'm showing you 4 rows. The first one is the DNS results, and the rest of them is basically the results obtained from the models. Okay, What I'm showing is a scatter plot of the flame surface density. So it's a grad C filtered as a function of grad C bar. Okay. So, and this relationship is usually described by a wrinkling factor. Okay. So that the solid line here shows you when the wrinkling factor equals 1. And then I go from a small filter size to larger filter size here as I go from left-hand side to the right-hand side. So if I just visually compare the DNS graph with what the model predict, I can see the difference immediately that, you know, you have a lot of scattered points here, especially when you go to larger filter sizes. But then when you look at the models, they don't show you the same kind of behavior, all right? But it looks like that the models are not bad when you have a small filter sizes. Like, you know, when delta equals 0.5, you can see that the, you know, it's okay. It's not too bad compared to what you have in the DNS. So one of the weaknesses of the models is this region here. So when grad C bar is close to 0, and this is where you have annihilation events happening, the DNS gives you very high flame surface density, and obviously the models are not able to predict that because these models, they just assume flame turbulence interaction. They are not considering any form of flame-flame interaction in their framework. Okay, so now let's look at the generated sound by these models and compare them with DNS. So I'm showing you pressure fluctuations, sound pressure level, and a zoomed in version of the sound pressure level. And from top to bottom, we increase the filter size to see how this impacts the results. So what is interesting is that if you use DNS to calculate that factor, the surface average displacement speed, and then apply different modeling frameworks, you don't see much difference between different models. So you can see that the DNS and the predictions by the models, they are actually okay. Also, in the previous slide, we saw, you know, large differences in some parts, but it seems to be okay. And the question is why, what's happening here that they don't do much? If you look at the next graph, in this case, what we do is basically replace that displacement speed term, like that surface average displacement speed term, by the common models which are used, like, you know, rho USL. Usually we assume in the literature that rho USL is a good approximation for the surface average displacement speed. Now you start to see the difference. You can see that all of these models, they underpredict the DNS spectrum, okay? And when you look at the pressure fluctuations, the difference is actually quite different from what we saw before in the previous slide. So what does it mean? It means that you know, all the effort we put into developing better models for the wrinkling factor, it's actually good, but we also need to dedicate some time to model the surface average displacement speed, because when you have a turbulent flame, obviously that surface average displacement speed can vary. It's not going to be just equal to SL, all right? So that was one of the conclusions that we drew from that study, that we should spend some time to think about the modeling framework and perhaps you know, get the balance right in terms of where we should put the effort in. Okay, so the next step. So as you can see, we are trying to increase the complexity of the problem. We started from laminar flames, and now we move on to a real burner. So this is a rig which was which was developed by NTNU. They've done some experimental work on that. It's basically a rig that can operate at elevated pressures, so we can go up to 2 bar. And they also tested hydrogen natural gas mixture. So We, in collaboration with Siemens Energy, we had a project to simulate that burner and try to understand whether we can capture azimuthal combustion instability in this burner, okay? So we have chosen 5 cases here, and I'm gonna just show you some of the key findings from that study. What we're looking at here is the sound pressure level comparison for 3 cases. So you can see that equivalence ratio is 0.8. I'm having 100% methane here. From this figure to the next one, I'm changing the equivalence ratio, okay? And then I keep the equivalence ratio the same, but I increase hydrogen percentage in the mixture in the last figure here. The black line is the experimental sound pressure level, and the colored lines are the numerical ones at different locations inside the burner. So what you can see is that for a range of frequencies up to about 6,000 hertz, we can predict the peaks, not, you know, the amplitude is not perfect, but we can actually, the frequencies of peak emissions can be captured from the simulations. But obviously, as you go to higher frequencies, more than 6,000 hertz, you get a large deviation from the experiment. And one of the reasons for that is the dissipation of the numerical scheme. What is interesting for us is that 6,000 hertz, if you look at the Struhal number, which is not easy to define in this case, because this burner is not just a round jet flame. You have a bunch of V flames sitting next to each other. But roughly speaking, that 6,000 hertz is equivalent to a Struhal number of 1. So that's, you know, consistent what we saw from DNS. Okay, so it looks like that we have a problem in terms of capturing that part of the sound pressure level when it comes to larger dissimulation. So now if I look at, sorry, I forgot to mention that those 3 cases were still stable. But if you look at the 2 other cases, equivalence ratio is the same, but hydrogen percentage is different. Interestingly, for the unstable cases, we can get a reasonable agreement for that range of frequency. So not only the peaks, but also the amplitudes can be predicted well by the simulation. Again, we have a problem above 6,000 hertz. So what we concluded is that it looks like that when you have an unstable case and we have large pressure fluctuations, the simulation are able to capture those large pressure fluctuations, and they kind of dominate the dissipation errors that you might get. But when you have stable cases, the fluctuations are relatively low, and therefore there might be a competition between the physical sound wave and the numerical sound wave. Okay. Now I'm going to move on to the next topic, and I understand that I've been talking for about 45 minutes, so I'm going to wrap it up quickly. So this is CO emission due to flame cooling air interaction. So again, we started from a very simple 2D problem. In this case, what you have is an inlet on the left-hand side. So a mixture is coming in. We have a flame which is anchored at the inlet, and we have one hole which is injecting cooling jet into the flame. All right, so the purpose of the cooling jet is to protect the wall, but in this case, we just wanted to see how flame cooling air interaction is going to impact the flame dynamics as well as CO emissions. In this setup, we were able to look at the impact of several parameters. So blowing ratio, basically how hard do we blow into this flame? Struhal number, how much we excite this flame, what range of frequencies do we use? And also we were able to change the location of the cooling hole to see what impact it has. And finally, we compared air and nitrogen to see if they have any impact on CO emissions. Okay, so I'm going to just show you the results the animation for one of the cases. And the thing that I want to highlight here is that the graph that you have here is one of them is the heat release rate, and the one on the right hand side is the CO emission. What you can see is that you can get a range of interactions with the wall. So the flame can be parallel to the wall, depending on where in the cycle is, and it can be completely perpendicular to the wall, which is quite interesting. So you know, that range of interaction can help us in terms of understanding what might happen in a turbulent flame. So the results I'm showing here is the CO emissions close to the outlet. So X plus equals 6 is that location here, okay? And what I'm showing is how the mean of YCO varies as a function of Y plus, which is basically that Y-axis here, all right? So the only thing I'm going to highlight in this graph is the impact of blowing ratio, because I think that's the most interesting one. So you can see that if I compare blowing ratio of 3 and 5, the profiles are not that different. But when I blow harder into the flame, I get a slightly more CO emissions. And when we looked into the results a bit more, what we saw was that when you blow harder, the quanta effects makes the jet to be closer to the wall, and that change in the dynamics is going to impact the CO profile downstream. So, so it's not just about how the cooling jet interacts with the flame, it's also about how the cooling jet interacts with the wall, okay? That can change your CO emission profiles at the outlet. So another interesting observation was, if I look at it in terms, you know, with the modeling point of view, one of the parameters, you know, the important parameter we are interested in here is the CO emission. And if you look at the CO thermochemical states, so I'm showing you YCO as a function of temperature here. And the scatter plot is basically the DNS results, and the lines are, you know, you've got different flamelets at different equivalence ratios depending on the cooling air that you have in the mixture. So you can see that the scatter plot kind of is covered by all of these curves, but the color plot here is actually showing you the equivalence ratio. So depending on the equivalence ratio, these points follow the corresponding laminar case, okay? So when you go to very lean conditions, so when the dilution level is quite high, the picture gets a bit more complicated. So you have this horizontal branch too, that we realize is actually related to quenching of the combustion product downstream of the interaction point. And that's where basically the heat loss becomes quite important, and that's gonna impact your CO thermochemistry. All right, so again, the question is, does this happen in a turbulent flame as well? So the study we did was to actually combine two problems into one DNS setup. So we had a channel flow, two flame branches interacting with the turbulence coming from the inlet. And on the top wall, I have a slots that injecting cooling jet into the flame. And then on the bottom wall, I have nothing. The flame is interacting with the wall without any cooling air, okay? So if I look at CO thermochemistry again, and if I color it by that dilution level or local equivalence ratio, I can see actually a very nice agreement. Like, you know, as I change the equivalence ratio, you can see that these lines are also able to explain the effect of equivalence ratio and thermochemistry. When I look at the top wall, which has the interaction of cooling air with the flame, okay? If I look at the bottom wall, which is flame wall interaction, there is no way I can explain it with the laminar, with the flamelets, okay? So I have a problem on the bottom wall, but on the top wall, it looks like that the cooling air is actually make the flame to behave more like a laminar flame, okay? So what does it mean in terms of modeling? So if I generate flamelets based on temperature and equivalence ratio and apply to my DNS to estimate YCO based on that, what I get is a comparison between my DNS YCO and also my estimated YCO. And this is the graph that I've got on the left-hand side is actually showing you that comparison at a location which is close to the outlet. And if I look at the time average, I can see a really good agreement. So what that means is that for this study, the assumption of having flamelets describing flame cooling air interaction is actually a really good assumption. It's even better than what we had for a laminar flame. However, that's not the end of a story. Obviously, you need to go to high Reynolds number to make sure that this assumption is still valid. But the results that we get so far is quite encouraging. So even if the assumption doesn't work as well, it seems that the flamelet assumption is a better assumption when you have a flame interacting with a cooling air rather than just with a relatively cold wall. So this is my summary slide, and hopefully by the end of this presentation, I was able to convince you that the perturbed laminar premixed flames are quite useful. We can use them to study flame characteristics in a systematic manner. So having a range of frequencies allows you to look at how the flame responds depending on the time scale of the flow. And that can be quite useful to get to see how different events can happen and how they contribute to the flame behavior. And also you can think about how to design the turbulent flame to study those phenomena and to see if they also happen in a turbulent flame. Another advantage of laminar flames is that they are computationally quite cheap, and that helps us to explore a large range of parameters in these cases. And I think that we can start to think about developing and validating new models based on these flames, as well as obviously trying these models for a turbulent flame. So I'm going to put up my acknowledgement slide. Obviously, what I presented today is teamwork. My colleagues from the University of Melbourne and industry, so Sandeep Jella from Siemens Energy, he's been quite helpful. We had a very close collaboration on the thermoacoustic instability stuff, and also Evet Hawks from UNSW, Benedict Cunard from Fairfax, and the current and former PhD students who've done most of the hard work in this presentation. And obviously the funding bodies and those who gave us the computational hours. So hopefully it wasn't too long. So I'm happy to take any questions you might have. Thank you.
Okay, thank you very much, Mohsen, for your very nice presentation. Okay. So now we will move to the Q&A session. Okay. So is there any questions from the audience and also the panelists?
I have a question.
Thorsten. Yeah, please go ahead.
Yeah,
yes.
Thank you for the interesting talk. I have a question about the flame pinch-off. You mentioned hydrogen flames at the beginning. So I assume when you run DNS, you have detailed transports. I heard different accounts about the importance of Soré diffusion or thermal diffusion. So some people say doesn't play that much of a role. Other people say even approximate Soré diffusion is a no-go. You need to have the full multi-component Soré diffusion. Do you have experience with this, especially for pinch-off and these types of local effects?
Yeah, look, that's a very interesting question. So when you think about Soré effect, for example, is when you have, for example, we have looked at it in the context of engine simulations. And when we wanted to generate lookup tables for the laminar flame speed, what we realized is that for hydrogen, if you include it, gonna get a flame speed at engine relevant conditions, which is about 5% difference compared to when you don't include it, okay? So that's gonna impact your laminar flame speed, 5%. And you know, one of the theoretical studies we've done in the past is to show how the flame key parameters impact these flame pinch off or, you know, flame annihilation events. And the laminar flame speed is a very important parameter when it comes to these events, right? It's probably the most important one. So we can then draw a link between what I mentioned from engine simulation studies, like, you know, if it's going to impact your laminar flame speed by about 5%, it might have even a larger impact in a flame interaction event, because flame acceleration is not just not driven by the laminar flame speed, it's actually multiplied by the laminar flame speed. So if you have a lot of acceleration, then, you know, that 5% can amplify to a much bigger event. But we haven't done that, you know, simulation to do the comparison. This is my, you know, a speculation based on what we know so far. But very good question. Yeah.
Okay, and then maybe just one comment. When you showed the graphs of the sound pressure levels, for the methane case at 5.65, you had a good agreement between the measurements and the simulations. And I wonder maybe if this is also an effect of the local flow chemistry interaction, because at these conditions, you should have a Markstein number of 0. So maybe the good agreement has something to do with, I don't know, pressure or flow interactions with the local flame dynamics and then the diffusive reactive balance.
Okay.
Just a blind guess.
No. Okay, no, that's a good point. Yeah, thank you. Yeah, we can look into that. But yeah, I just want to highlight that when it comes to simulating a burner, there are lots of different things happening inside that burner. Of course, And you know, at the end of the day, this is what we want to simulate, right? We want to simulate a real burner and see what happens. But there's so many factors that can impact the end result. So that's why I like to approach them from very fundamental view first before, you know, simulating them. Okay, thank you. Excellent questions. Thank you.
Okay, thank you very much. So we have one question from the audience. So thanks to Professor Talei for your wonderful presentation. So we'd like to ask you about how to distinguish what chemical processes are responsible for the CO scatter in different branches. Yeah.
Okay. So that's a very good question. So obviously, when you have flame turbulence interaction, it's actually hard to say that look, you know, we have a bunch of flamelets that are present and they just interact with turbulence. So that assumption has inherent limitations. Okay. And that is partially responsible for the scatter that we get. The other thing is we do not include the strain effects in you know, plotting the flamelets that we have. They were basically free strain flamelets. We do not include the curvature effects that, you know, you can also include if you like. So in terms of the, you know, the physical mechanisms, the flamelets that we have used, they are limited. And that can be one of the reasons for seeing a scatter and not a, you know, great agreement.
Okay, yeah, thank you very much.
Okay.
Yeah.
No worries.
Yeah, and then Professor Jensen also had questions. Yeah, Professor, maybe you want to ask.
Hello.
Hi, Professor Talei. I'm fine. Thank you for the very nice talk. I have a question about the cooling air jet. Basically, for the flame wall interaction, there is a flame quenching when the flame touches the wall. So I'm wondering whether the air jet can quench the flame locally if the flow speed is fast enough.
Yeah. So look, a great question. So if you actually blow really hard into the flame, you know, we've done that in a laminar flame. Remember, I showed you a slide which was our former PhD student playing with the flame and getting the flame to dance. If you actually blow really hard, you can actually get the flame to become unstable, and you get local quenching of those, you know, some parts of the flame, and you can see, you know, high CO regions as a result.
Okay.
We didn't look into that part because, you know, we're focusing on understanding what happens under a controlled condition, but the cooling jet has kind of a, you know, is a very complex one, because if you provide air, one of the things that it will do is going to oxidize your CO.
Mm-hmm.
And this was one of the mechanisms that we found. So like we found that, you know, having cooling air is actually helping your CO emissions.
Okay.
However, as I said, if you blow really hard, then you get quenching effects that is going to create regions of high CO. So it depends on, you know, how hard you blow into the flame. Yeah.
Okay. And I have another question about the jet. How do you choose the angle? I see there's an angle between the jet and the wall.
Yeah, so that the angle is determined by the inlet velocity. So what we aimed for was to actually simulate a laminar flame, you know, which is affordable computationally. So we selected the domain size, and then we basically set it up such that, you know, your inlet velocity can create that flame angle, which, you know, you can cover a large range of the computational domain. Okay. So that was basically determined by the limitations of the computational cost. Yeah. And the inlet velocity just determined that angle based on the laminar flame speed. It just was the outcome.
Yeah, that I understand, but I see that there's the flow direction of the air jet from the wall. There's an angle between the.
Oh, you're talking about the jet. Okay, sorry. I thought you're talking about the flame itself. So that one, we looked at what is done in industry, like for example, you know, what range of blowing ratio is more common, and you know what angle is usually used. So we tried to actually match some of the conditions. So we decided to use that angle, which is close to what happens in a real combustor.
Okay.
Yeah.
Okay.
Because the thing is, I mean, there are different ways of cooling the combustor wall. And one idea is to actually shield the combustor wall against the flame. And if you have an angle, if your flow comes at an angle, it's going to create that shield quite nicely. But if it's a vertical hole, you might not get that effect, you know, as effectively.
Okay. Okay.
Yeah.
Thank you.
No worries. Thank you.
Okay. Thank you. Any more questions from the audience and also panelists? Okay, so maybe I ask one question for the first example. So there,
Sure.
what is the computational cost for you to capture the unsteadiness for the laminar flame, right?
Yeah, sure.
Yeah.
Yeah. So for the laminar flames, the computational cost, because that study was done quite a while ago, right?
Okay.
I have to think about how much hours it costs, but I can give you an idea about the turbulent flame, and then we can kind of estimate what happens in a laminar flame. So the turbulent flame cases that we did, they cost us about like 1.5 million hours on the supercomputer that we have here at Melbourne.
Okay.
And the laminar cases is an order of magnitude lower, at least lower than those cases.
Okay.
I would say even 2 orders of magnitude lower than the turbulent case.
Okay. Yeah.
Yeah.
In the presentation, you also present the experimental results, right? I think one slide. So did you compare your simulation results against the experiment data?
For which case are you?
For the first example, I think you showed the dancing laminar flame there.
Yes. No, we didn't do that for the laminar flame because although the laminar flame is laminar in the experiment, simulating it with DNS is actually very costly. The reason being is the diameter.
Okay.
So the burner that we had a diameter of 25 millimeters. And that's quite large for DNS. So usually for DNS cases, the diameter is about 1.1 to 3 millimeters. And we didn't validate it. We just relied on DNS being DNS. Okay. But for the turbulent case, we have some plans to do that because we have designed a new burner which the diameter is like 5 millimeter, and we are planning to do a DNS of that case.
Okay. So for these simulations, you use the OpenFOAM or your in-house code?
Now, for DNS, we use the NT-Mix and NT-Mix Camkin. This is originally developed by Cefax. So Professor Benedict Cunot is my collaborator, and we're working together to improve the capability of the software. So it's an in-house code, basically.
Okay.
But yeah, for LES, we use the different codes depending on the problem.
Okay. Yeah. Okay. Yeah. Thanks.
Thank you.
Yeah. Any other questions? Okay. Seems no more questions. Okay.
Okay. Now.
Yeah.
Excellent questions so far. So appreciate that.
Yeah. Okay. So for all the panelists, I invite you to open your camera and thank our speaker again. Okay. Yeah, thank you, Professor Talei, and thanks everyone. Okay, joining us.
Thank you for having me.
Yeah, okay. Thank you, and see you soon.
Yes.
Okay.
Yeah, absolutely. Looking forward to it.
Yeah. Good evening. Okay. Yeah.
Yes.
Bye.
Thank you. All right. Bye.
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 Bye.